Decoders Revisited. Please take it away.
Thank you. Thanks, everyone, for showing up at 10 in the morning, including myself. Glad we all got here, and thanks for all the Stanford people for coming up a second day. So I'm going to talk about field-based decoders. I'll explain what that means in a sec. But kind of more broadly, what the talk is going to be about the ongoing search for fast and scalable error correction schemes for topological quantum memories. Okay. And the topological quantum memory I'm going to be focused on this talk is the tort code. Okay, so given things how it went yesterday, I decided I didn't need to do any kind of explanation about what the tort code is. Suffice it to say, it's a two-dimensional stabilizer code. It has anyons, it has two types of anyons. And when we perform error correction on it, let me move my cursor out of the way. When we perform error correction on it, the name of the game is measuring the stabilizers and moving the anyons around in a way which prevents things like this from happening, right? Where anyons either diffuse around a cycle of your torus or move off to opposite boundaries of the surface code. Okay. So talk is going to be about ways in which error correction that prevents this kind of process from occurring can be accomplished in fast and scalable ways. Okay. So here's how error correction in the tort code is currently done. You have this is the laser pointer. You have a quantum computer in which the tort code is living, and measurements are performed, syndrome measurements are performed on the tort code, and the results of those measurements are fed outside the quantum computer to a classical computer, which takes the outcomes of those measurements and does some data processing on those syndrome measurements to determine a appropriate feedback operation to apply, and the instructions to apply that feedback operation are then transferred back into the quantum computer. So there's this loop that's going on here. And here as proof of that this is how it works, here's a picture of Google's device. So here the tort code is living here, right, in the DIL fridge, and all of their syndrome measurements being performed, and all those measurements go outside to this giant stack of computers, which is sitting outside of the quantum computer at some other spatially distinct location. Right. Okay, and then since I think everyone is theorists, I'm just going to claim that this is not a scalable approach towards doing error correction, right? So the reason being is that you have to take all the data that you acquire from the syndrome measurements, transfer them out to non-locally to some separate location, do a bunch of data processing, and then transfer the results back. And the latency and the finite speed of data processing that you incur when you do this actually matter, right? So I'm not actually going to spend any more time than this dwelling on this issue because I'm not a hardware person, but just if people are interested in understanding the kinds of processing speed and latency requirements that you need to get around, you can look at this, for example, this paper from Google. The salient points here are that the decoding that you're running needs to be fast, so it needs to be parallelized. And let me just say that the current protocols, which are based on minimal weight perfect matching, are not scalable in this definition. Okay. So what we would like to aim for, especially as theorists, we would like to aim for a completely parallelized error correction scheme where the error correction is kind of going on inside the quantum computer rather than in the separate rack of classical processors outside the computer. Okay, so this is kind of schematically what we're going to be aiming to construct. We have our qubits in a grid, and then each of these boxes here is made to represent a sort of local classical data processing device. What each one of these guys does is it measures the syndromes in its vicinity, takes the results of those measurements and does something with them, and then locally applies feedback based on the results of those measurements. Okay, so if you accomplish error correction in a scheme like this, you've constructed what I'm going to call a cellular automaton decoder for the tort code. For the condensed matter people, you might call this a noise robust phase of matter. Okay, but this is the kind of construction that we're aiming for. So for the purposes of this talk, when we think about making such a construction, there are a few things that we must have, that we're going to be required to have. One is that I'm going to require all of the operations performed to be local in space-time. So this includes all of the measurements, all the quantum operation. It also includes all of the classical data processing and classical communication. The other thing I'm going to demand for the purposes of this talk is translation variance, at least in time. So I want all of my entities, my data processing units here to just be implementing the same thing at every time step of my simulation. And then I'd also like that the number of classical control bits at each site in my system not be too large. So for this talk, I'm going to want it to not grow faster than, say, a logarithm of the system size. Okay. Things that would be nice in addition to the must-haves are, I would like, ideally, if this decoder operated asynchronously. So meaning that each classical data processing device in the decoder could kind of operate independently at a clock speed which is independent of the other processors. I would also like the error correction scheme to be translationally invariant in space. And it would be nice if I could get away with having, say, only order 1 number of control bits per site, so independent of the system size. Okay. One thing that I'm completely not going to care about are errors in the classical control bits. So I'm going to assume that the only errors that arise in my system are those in the quantum hardware, not in the classical part. Okay, so this is the setting for the talk. Okay, and then when I speak about doing error correction, we're going to be focused on 2 different types of error correction tasks, and I'm going to give them the following names. And I apologize if you don't like the names, but we're just going to use these names for the purposes of the talk today. The first task that we're performing is offline decoding. So in this task, we have a logical state. It's subject to some noise of some strength p. We perform 1 round of, in our case, perfect syndrome measurements. And then we ask if, using the results of those measurements, we can correctly recover the input logical state, or recover it at least with high probability. Okay. That's one task. The other task that we would like to perform is online decoding. So in this task, we continuously subject the system to noise. We continuously make imperfect, now, syndrome measurements. And we ask how long the input logical state is, the memory of that, how long that remains in the system. So more precisely, how long can we run this dynamics for such that at the end of our dynamics, the input logical state can be recovered by an offline decoding procedure. So this task is kind of really what we're interested in most at the end of the day. But it's strictly harder than the offline decoding task. Okay, so I'm going to be talking about both. Okay, so I hope that the vocabulary here is set and makes sense. Okay, so the existing decoders that we use for the Torque code, for example, the one that Google was using in its recent experiments, are based on doing some form of minimal weight perfect matching, usually in some optimized, kind of efficient, smart way. But in any case, it's doing minimal weight perfect matching, and approaches like this always involve some amount of non-local classical communication. Maybe a modest amount, but for us, it's always going to be too much. And they're not going to fit within my definition of scalable for the purposes of the talk. However, there are other approaches, and I'm going to just briefly review a few. So maybe the first that people would be familiar with is Harrington's decoder. So Harrington's decoder was proposed by Harrington back in 2004 in his thesis. It follows a sort of a hierarchical RG-inspired approach towards doing error correction. It fits our requirement of being completely spatially local, but it has some downsides for us. One is that it's not translation invariant, neither in space nor in time. There's long-range feedback in time. It requires all of the processors operate synchronously. It doesn't allow for continuous time operation. The threshold, maybe there's some, you have to be a little bit careful in actually proving that there's a threshold for this code, and et cetera. So I'm not going to go into detail about this, but this is one you may have heard of. If you were here yesterday, you also heard about a new construction based on hierarchical one-dimensional classical memory. Since Shankar already gave a good talk on this, I'm not going to go into any detail. Suffice it to say, this gave you a local scheme for doing error correction, one with a provable threshold. But at least today, we're going to be looking for something that is translation invariant in 2 dimensions. And we would also ideally like to have something which doesn't require this synchronization. Okay. These 2 schemes that I just talked about are based on some kind of hierarchical RG-inspired approach towards doing error correction. But there's a third kind of very natural approach to try, especially as a physicist, which is the following. You just get the classical control system to induce a form of attractive confining interactions between anyons to make them pair up. Okay, so we imagine the classical processors in my system create some sort of like gravitational potential that looks like this, and it wants the anyons to be attracted to one another. Right? This prevents, if the anyons are confined by such an interaction, it prevents them from moving around the system and creating a logical error. Okay, so this approach was, like, I think first suggested in the famous Dennis et al. Paper, and there's been a long history of people thinking about similar ideas. I'm not really going to go into much of the history. I'm just going to briefly review sort of the two papers here at the bottom, which are sort of most relevant to the construction that I'll be discussing today. So these candidates are, I'm going to call field-based decoders. They were introduced in these two papers, and I'm going to now briefly describe how they work. Okay. So they work in the following way. What you do is you place a scalar field phi, so just a real variable, at each site of your lattice. And you update phi according to some equation that would look like this. So for example, in Harold et al., they chose this Poisson equation. So it's a Poisson equation with sources at the locations of the anyons. And when you have a field phi which satisfies this differential equation, it creates a potential landscape that looks like this kind of gravitational attractive interaction that you want. When this phi is then computed by your classical array of processors, you apply feedback on the system by taking anyons and moving them in the direction of the field gradient. Right?
How many dimensions is the Laplacian?
I haven't told you yet. We would like it to be in 2 dimensions, of course. Right? But I haven't told you yet. But we can try. This is definitely an approach we can try, right? And this is sort of the most natural thing you would do as a physicist. Before getting into detail about exactly the dimensions of the Laplacian is and et cetera, let me just tell you what they found. So they did numerics on schemes like this. And they found a threshold in their numerics for this offline decoding problem. And they found something that looked like a threshold for the online decoding problem. Yeah?
So like these fields, are they stored locally?
Yeah, they're stored locally. So you have, let me go back to my picture, right? So there is a phi living at each of these like blocks.
So the model is that the control bits, they're not read-only. Like you can.
They are readable and writable, yes.
Oh, and the classical writing is free.
Yes. So if you really like eventually there will be a model where you only have order 1 bits per site. So we're not going to worry about that.
Okay.
Yeah. But yes, let's say it's free. I mean, the cost that you pay in doing these things will end up being like log of L, which is negligible for me, but yeah.
In the offline setting where you just apply some error that doesn't know anything about the field beforehand,
yeah.
How does the field then help you to do error correction?
Yeah, so you can imagine in the offline decoding problem?
Yeah, in the offline decoding.
Yeah, so the system is instantiated with some pattern of anyons, and then the field profile is grown from those anyon locations. And then once the field profile spreads to the locations of other anyons, a gradient is established, and those anyons can then move in the direction of that gradient.
Oh, right. Yeah. So how do you know when to stop? Like, is there like some parameter which kind of does like you wait this amount of time for this field?
For the offline decoding?
For the offline decoding, yes.
Yeah. So you would the way we're going to do it in what follows is we're just going to initialize our anyons with no field anywhere. We're going to let the field grow from the locations of the anyons. The anyons are going to move around. And then once all the anyons are gone, we're going to stop.
So for the offline decoding, why do you care about the velocities?
We want to make the decoding fast, basically. So every update step of the field is going to be 1 time step. So you might think that one way of approaching this problem is let's first find an offline decoder that works as fast as possible, and then let's run that in the presence of transient noise now and see how that goes, right? But in order for that approach to work, the offline decoder first has to work very quickly. Okay, so yeah, is this setup good? So as I was saying, they did numerics and they found things that look like thresholds for both error correction problems. The drawbacks is one that you picked up on is that they had to let their field phi actually live in 3 dimensions. So they had the toric code as a 2-dimensional slice, and then the field was actually propagating in 3 dimensions. This was done in order to get the kind of right force profile for this field. They required that it live in 3 dimensions. And the other drawback of their proposal, at least for as far as I'm concerned, is that the update speed of the field phi had to diverge as the square of the log of the system size. So this was not actually scalable in my definition because the update speed had to diverge.
Sorry, I'm missing something because maybe I didn't understand what you're saying. But these potentials that you're creating, are they just a proxy for finding shortest distances and collapsing or something? Is that all that's going on?
Yeah. So you could imagine. I'll get back to exactly what they're doing in regards to like shortest distances between anyons, but they're kind of supposed to be some proxy for doing minimal weight perfect matching in a local way, right?
Yeah.
We'll see the exact way in which that does and does not work in a sec.
And so I was confused by what you said about 3 dimensions. If that's all that's going on, where does another dimension come in?
Yeah, so it's a bit technical. So they want I'll get into this in detail in the second part of the talk, but you need the attraction strength between the anyons to be some particular. You can't have it be too strong, and you also can't have it be too weak. If you just look at this Poisson's equation in 2 dimensions, the attraction is a bit too strong. If you go to 3 dimensions, it becomes a little bit weaker, and that's good for doing error correction. But the reason why that is so will become clear later. I don't try to understand why they had to go to 3D yet. You'll understand later.
Having to go to 3D was an actual physical thing, like you actually had to run this on a 3D system, or you just have to...
No, you could have a large number of classical degrees of freedom at each site and then pretend that there's a dimension hidden in these degrees.
Just weaken the field? Like I'm still not understanding the role of this.
Yeah, so if you have a Poisson equation like this in d dimensions, the strength of the field is fixed. Like you don't get to tune that.
Yeah, because you want to write it that way, but you can write down anything you want. This is not an actual physical. So
yeah, you can write down. Okay, you can write down. We're going to be indeed writing down something different, right, to solve these problems. But I'll tell you exactly what you want to write down instead of this in a sec. Yeah. But one of the indeed you don't want to write down this because of these 2 problems. Okay, I'm just describing what was done, right? The most natural thing for a physicist is Poisson equation, and then we'll have to do something different. Yeah.
So do you find the log square divergent speed?
Yeah. So speed is maybe not a good word to use, but what I mean is that you need to do log squared field updates for every 1 anyon update. So the log square, really, morally speaking, I'll explain exactly why you need this in a sec, but morally speaking, the fields need to update infinitely faster than the anyons update. For us, that's bad, right? Things to be happening fast. So let me try to explain why this is true, right? So what we're going to do in the rest of the talk, first I'm going to explain why these issues arise and how we fix them. This is kind of maybe a kind of minor engineering part. Then I'm going to present some good news for the offline decoding problem and some bad news for the online decoding problem. So let's first do the first part. So let's first fix this divergent communication speed. Okay. So where does this come from? This comes from the interaction between an anyon and the field that it itself generates. Okay. So I'm going to try to illustrate this schematically as follows. So suppose I have 2 anyons. They set up some potentials, some values of phi in their vicinity. And as I said, the anyon moves in the direction of the field gradient, right? So this anyon is going to see that there's a gradient of the field caused by this anyon, and it's going to move to the right. But the problem is that once it moves to the right, now the gradient it sees is actually completely determined by the field that it left behind, right? So it's just attracted to the image of where it was in the past, right? Because the field hasn't updated yet. And this is a problem, right? We want the anion to move over here, but it's getting attracted to its own field. Okay. So what needs to happen is that the field needs to update very fast to take into account the anion motion. So when the anion moves, the field needs to update, and locally the field needs to completely equilibrate so that the anion doesn't see its own field. Okay. Does that problem make sense, right? So in electromagnetism, we don't have this problem because we have gauge invariance, and the divergence of the field is fixed to the location of the electric charge. But here, the anion and its field are separate entities. One is existing in the quantum system, the field is existing in the classical system, and they're not tied together. And the fact that they're not tied together causes this problem. Okay. So the solution to this is to make the fields update much faster than the anion locations. And how fast that the updating needs to be done turns out to be log squared of L if you want to get error correction done. The important part is just that it has to diverge.
But where does the system size come in? This problem looks like it happens with just 2 anions as well.
Yes, so the system size comes in for the following reason. You need to set up attractive interaction between 2 anions whose distance is at most log L apart, right? That's the biggest pair the noise will create. So you need to worry about an interaction existing out to that range. That means the signal you're going to be getting from your partner anion is like 1 over log L to some power, and then that's where the log squared L comes from. I'll give you a more detailed argument later.
So at early times, it won't really be a problem.
At early times, it won't be a... Well, the thing you always care about is what happens to the largest pair in the system, right?
Well, but the things that are annihilating at early times are the things that were close together initially anyway.
Yeah, that's true, but you need the guys that are far apart to start attracting each other, right?
Right.
So that needs to be... That can only be done through this very fast updating. Yeah. Okay, so how do we solve this problem? Well, we can try different types of ways of updating the field. Right? So more generally, let's suppose we update our field by some differential operator, which is sourced by the anion locations, right? So for example, one thing you might try is, let's take this differential operator to be the wave equation, right? dt squared minus dx squared, right? In this case, the signals emitted by the anions will just spread outward at the speed of light, and the anion won't be able to catch up with them because they're moving outward at the speed of light, okay? To kind of formalize that a little bit, if you want to avoid the interaction between the anion and its own field, the Green's function for this differential operator needs to have support only on the light cone, so or on the boundary of the light cone, if you like. So the signal sent by the anion needs to just propagate away from the anion and not leave any residual signal at the anion's location. Okay. Unfortunately, the only choices of differential operator here which have this property are wave equations in odd dimensions. Okay. And we're interested in 2 dimensions. So in 2 dimensions, you'll be familiar with the fact that if you drop a stone in a pond, ripples remain at the location where the stone was dropped for all times. And this, in 2 dimensions, prevents wave equations like this or any other linear differential equation from working as an update rule for the anion locations.
Why does it have to be linear?
Well, this is saying it's not going to be linear, right? So we're going to have to do something nonlinear. Indeed. So what do we do? Okay, well, it's not really super important. It's just engineering details, kind of as was suggested earlier. Well, why do we have to do a PD? There are many other things we can try. Okay, so there are many other things, and some of them work. So let me just tell you very briefly a scheme you could use. So let's imagine for the purposes of visualization, we're in 1 dimension. Anions are going to be sending out sort of right-moving messages and left-moving messages to their partners. These messages are going to be, say, real-valued numbers on each side of the lattice. And you choose some update rule such that the message profiles equilibrate to some power law. Okay. As you suggested, the update rule that you choose is going to be nonlinear. Okay. So if you want the interactions to fall off as 1 over a distance to the power alpha, you can choose, for example, this update rule. So these fields are sourced at the location of anions, and they are updated away from anions according to some nonlinear update rule. Okay. What this results in is a potential profile being set up like this. So I have an anion here, say at this site, and it creates a left moving field, it creates a right moving field, which decays with some power, and it creates a left moving field, which decays with some power to the left. Okay, you just choose some particular automaton rule that does this. And if you have another anion here, what's happening is this guy sends out left moving messages to the left. This guy receives those messages and then starts moving to the right, and vice versa for this anion. Anyway, the point is we're just not using PDEs anymore, and we're doing some type of nonlinear update. Some engineering remarks about this that I need to make. So you can come up with a message passing system that results in power law decay of interactions in 2 dimensions. Right? It's a little, you want things to be translation invariant and everything, so figuring out the details are a little bit annoying, but it can be done. If you want to get a linear superposition of forces from different anions, as you would get in this Poisson's equation, right? You want the force to be a sum of the forces you feel from all other anions. You need actually a large number of flavors of messages because things are nonlinear, and you need, in fact, log L flavors of messages. Let me not get into the details unless people are curious. And yeah, if you're bothered by the number of bits per site, I can tell you ways in which to lower these. But I think for the physics that is at play here, I'm not going to spend a lot of time dwelling on these details.
Sorry, I missed something. What
Yeah.
was the point of the 2 flavors? How are they being processed by the anion?
The left and the right thing?
Yeah. I mean, is it just is it treating them separately, or?
Yeah. So it's basically what you do is, as an anion, you measure the fields at the site on which you live, and you look at the difference of the right message strength minus the left message strength, and depending on the sign of that difference, you either move to the right or to the left. So if you're getting a lot of left moving messages, then you move to the right, because you know they've been emitted from some anion on your right. If you're getting left moving messages, then you move to the right. That makes sense. It's just so you just come up with some message passing. Basically, the point of these few slides is just to say that there exists some message passing framework that you can set up whereby the message strengths decay as some power law, and the message fields are instantiated by some local translation variant process. I think maybe the result is kind of more, it's not a very interesting result, but the result that this is possible is more important than the ways in which it actually is.
And the role of the multiple colors, apart from the quadrants issue.
Yeah, sorry. So suppose we want the force at site X to be like a sum over anion locations of like the direction to that anion location times some power law, right? Minus X to the alpha. If we want a linear superposition like this, we can't use this nonlinear equation, right? The messages are kind of going to interfere with each other. So what we do is we have an anion here starts emitting messages of flavor A. Then if it hits another anion, these messages go through this anion and they become flavor A plus 1. And then they hit another anion and they become flavor A plus 2. And then when you're looking at the force that you experience as an anion, you add up all of the different message flavors. So the fact that your message identity is changing as you pass an anion allows you to superimpose these forces from different anions. Yeah.
Doesn't this imply that the number of bits you're sending is proportional to the number of colors, or at least like log? So like you need to index the number of colors.
That's right. Yeah. So that will be some log function of system size.
Of system size.
Yeah.
But you're saying you don't need to store it because like at the end of the day, the number of bits per size is like log or log of system size.
Log system size.
I see.
Yeah.
Okay.
So if you are bothered by that, I'm going to not be bothered by that for the most of the talk. But if you're bothered by that, you talk to me later, and I'll tell you how you can reduce it. Yeah. But yeah. Okay. So anyway, the point on of these slides is just to say that these issues of divergent communication speed and this 3-dimensional nature of the control system can be solved. Yeah.
Sorry, just a stupid thing. The velocity of the anion is proportional to the force of the accelerator, not the acceleration.
The velocity is going to be taken to just be. You can come up with any update rule you want. A nice update rule is you move in one lattice site in the direction that the force is largest, independent of the force's magnitude. So that's the rule we're going to be using, but you could design other schemes also. The reason why that's nice is that if you get a very weak force from your partner anion a far distance away, you still move at a large speed towards that. Yeah.
Did you hear anything special about the picture is one-dimensional when you talk about number of flavors?
No, you can same number of flavors in any dimension. The reason why it's log is that you only care about instantiating the interactions out to a raw log L radius. So you have to, in 2 dimensions, you have to, of course, it doesn't make sense for a message to pass an anion, so you need to do some more complicated engineering to figure out how to do the color changing, but we can tell you about it later. Anyway, this is kind of if we're not going to worry about log L bits per site, then this is, I think, the simplest way to engender these power law interactions. So it can be done, but so once we've set up these interactions, what do they actually do? This is kind of the more interesting question from the perspective of physics, right? So as a recap, the Harold et al., when they studied these, again, 3-dimensional guys with divergent communication speed, they found a threshold for, what they found in their papers was a threshold for offline decoding and also a threshold, albeit a smaller one, for the online decoding problem. And so let's now ask how well these now local finite speed versions work. So let's first talk about the offline decoding problem, the easier one. Right? So here's the setup again. As a reminder, we have a logical state. We apply some noise of strength p. Perfect stabilizer measurements are made, and then we attempt to recover the initial logical state. So in this problem, we care about 2 things. One is the decoding fidelity, f. So this is 1 minus the probability of making a logical failure during the decoding. And the other is how long the decoding algorithm runs for. So that's going to be called t, is the time for decoding to be completed. We definitely require is that the decoding fidelity, this should be a 1, sorry, not a 0. We require that the fidelity go to 1 when the system size is made infinite, as long as the error rate is small enough. Okay. And what we'd also like is that the decoding time grow as a slow function of the system size. Okay. We want the decoding to be fast. And the fastest it can be is log L. Okay, so log L is the size of the biggest errors that we expect to get in our system under this noise model. And since we're doing things locally, the fastest this can go is log L. Okay. This is what we're aiming for. Of course, just letting the anions randomly diffuse around without adding any attractive interactions between them doesn't work. Okay, this gives you a fidelity that doesn't care about L, and it gives you a decoding time which is diffusive, so scaled by L squared. So that's not doing anything, of course, doesn't work. But actually, almost anything else does work and does give you a good offline decoder. When I say almost anything else, I mean almost any attractive interaction between anions. Okay, so what I'm going to do for this offline decoding problem is I'm only going to use 1 flavor of message. I don't know if the flavor stuff really, I don't think I really talked about that in a way that really illustrated what's going on, but we're only going to use 1 flavor of message. We're not going to worry about creating a linear combination of forces from all the different anions in the system. We're just really going to care about the force being set up between anions which are closest to one another. And what this force is going to do is it's basically equivalent to a version of the following rule: move towards the anion that's closest to you. Okay, which seems like a natural thing to try. Yeah.
Can you talk about the physical difference between this kind of decoder and the renormalization group, so-called decoders? Isn't what one's doing there also basically,
Yeah. So we're trying to. I wouldn't say we're trying to do renormalization group, but the way in which the renormalization group decoders work is you have some collection regions for the anions, which is hardwired into the dynamics, and you kind of decide in advance a particular scheme by which anions are going to be grouped up and paired. Right? We want to do something which is translation invariant and local and everything, so we would like all of the different processing units to be doing the same thing autonomously, autonomously in time, and so we're trying to get anyons to pair up with their nearest neighbors, but we're not hard coding in any particular hierarchical structure to how that is going to happen.
But at a given time, there will be some characteristic length scale over which things will have.
Yeah, sure. That's true. And the way in which you would, well, I'll make a tiny comment about that kind of philosophy later. Yeah.
Just to clarify that, I'm following something really elementary. The claim that this is going to terminate sort of in log n time or log system size.
We want it to terminate.
We want it to. Yeah. That actually requires p to be high enough, right? To be, let's say, a constant. If p is
well, that requires it to be low enough, but yeah.
Well, if there are just very few of these.
Yeah. Okay. Log L really the best we could hope for is log L divided by log of 1 over p.
Yeah.
So this is the expected value of largest anion pair. Right? In the system. It goes like this. So the farthest apart anions that we'll have to correct are going to be that size. So we're not going to do any better than this, but we would be the best.
And you don't worry about ties in terms of moving towards them.
Yeah, if they're tied, let's just randomly choose a direction.
And
okay.
How can you tell that locally that there's a...
Oh, so locally okay. So what's going to happen here is that you get a force from your nearest neighbors. Well, the anions which are closest to you send out forces. If you move in the direction where the force is biggest, and if the forces are exactly cancel each other, you just randomly pick a direction.
And how do you make sure that as you're moving in that direction, that anion is not moving in a different direction?
Oh,
so
it may that may happen. Yeah.
So
you could if you wanted to make a very adversarial situation in which this kind of marketing would happen, then oh boy, I'm curious. You would do something like put an anion here, and then an anion here, and then an anion here. Something like this, but things like this don't come up very often. So our statement about this working in time log L is going to be a probabilistic statement. Meaning we can hope for the decoder to converge in log L time on average. We can definitely construct examples of configurations where it's going to take L time, but those will be rare.
And so on average, so what's the model in which it's on average? So what are you assuming is distributed how? So it's randomly...
Say on each link of the lattice, we create a pair of anions with probability p. So really what is the noise model is the p-bounded noise model that Shankar described yesterday. But you can imagine just IID noise on every link. String p. So yeah, we're going to be studying this kind of rule for the offline decoding problem. So here's a movie of this, how this works. So I just initialize the system in a random state. The colors that are being shown in the animation is the magnitude of the force that each anion feels, and the anions just move in the direction of the force. So they pair up in a way that looks like this. Okay, thumbs up. Okay, so when we do this, it's also interesting to study this decoding problem for the repetition code in 1 dimension. So basically, imagine all the anions just live in 1 dimension, and you could also study how the decoding works in that case. When you do this in 1 dimension, you find that there's a threshold for this decoding problem that goes to, looks like it's going to 1/2. When you just do this move towards the anion which is nearest to you. And the decoding time is indeed goes as log L. So you can see this in numerics. If you don't trust the numerics or you want things to be a bit more careful, you can prove that this log L result is obtained using some sparsity techniques developed by Gash. So you can look at how the noise is distributed at different scales and argue that anions at different scales get cleaned up in such a way that the expected time for the decoding to end goes as the log of the system size. And for the toric code, when anions live in 2 dimensions, there's again a threshold that you would find in numerics. The threshold, if anyone cares, is around 7%. So this threshold is a bit larger than the sort of the non-local model that was constructed by Harold et al. It's a bit lower than some other kinds of minimal weight, perfect matching RG inspired decoders, but okay, maybe the exact value of the threshold is not super important for this audience. And again, if you look at how long decoding takes to be completed in this model, again, it scales as log L, and this can also, again, be shown using this sparsity techniques developed by Gas.
Yeah, this is in the offline.
This is all offline decoding, yeah. Yeah, so just to summarize what was learned in the last couple of slides, maybe I flashed through a bit quickly, is that for the toric code, we have a local, spatio-temporally local offline decoder, which I didn't really describe the memory requirements on each site, but you can make it work with only order 1 bits per site. It operates asynchronously, and it converges in log L time. So this is, in some sense, the best that we could hope for for offline decoding. So these parameters can't really be improved. But what we really care about is the online decoding problem. So what happens in the fully fault-tolerant setting. And that's what I'm going to talk about now in the last part of the talk. So recall what the setup is. So in online decoding, errors are happening continuously at some rate. And the measurements that are being made of the state of the syndromes are unreliable with some non-zero failure probability. And what we want to know is the time that this active decoder can be run before a logical failure occurs, as diagnosed by some offline decoding scheme. Okay. So a first observation is that this move towards the nearest anion type of framework that we were using for offline decoding does not work when you're trying to do online decoding. Okay. And the reason for that, I'm going to just try to explain with this picture. So as I already wrote on the board, the maximum size of an anion pair that is added to the system by the noise is going to scale with L like this. The important point is that this is going to be infinitely large. And if we just move towards our nearest anion, we run into the following problem. So consider a system where we have this one large anion pair of the separation like log of L. The anions nearby, these two members of the pair, will, with high likelihood, just be locked in some small scale pairs created by the noise. And the anion which is closest to, say, this member of the pair will, with probability 1 in the thermodynamic limit, be a member of some bound pair nearby it, and not the guy that it's actually paired with in the system. Right? Does this make sense? Some people think it makes sense.
Can you just repeat the sentence, please?
Yeah, I don't know if I'm not going to repeat that sentence because it was a bit long and convoluted. I don't remember exactly what I said. But if you agree that what we need to do is this guy needs to be paired up with this guy, right? Okay. If we just move in the direction of the anion which is closest to us, the closest anion to this guy is never going to be this one. It's always going to be some random anion in some small pair that was created by the noise. The location of this closest anion is not correlated with the location of this anion in any way. Therefore, this anion is just going to diffuse. It's just going to move in a random direction. And that is as if you were doing no error correction. Yeah.
But the small ones will likely be, those ones will likely have been annihilated at earlier stages of the RG anyway.
Yes, but we're doing online decoding.
Oh,
so the small ones are always being created now, right?
If a small one is created right next to something that was supposed to be annihilated with something far away, then you're in trouble.
Yeah, but it doesn't have to be created right next to it. It just has to be created somewhere closer to it then, right? So when we did offline decoding, that logic was fine. These guys rapidly disappeared, and then in short time, we were actually able to see the guy we're paired with.
Maybe this can be viewed as like a screening interaction. Right?
Yeah, this rule, move towards your nearest anion, results in small errors completely screening the force that you're supposed to be getting from the guy you're partner. So for offline decoding, that wasn't a problem because they all got killed rapidly by the decoding. But with online decoding, this ruins the scheme. So moving towards the closest anion actually doesn't do any better than just randomly diffusing. So we can't do that. So that's why we want to have a interaction which is set up as a power law like this. So okay, we can't move towards our nearest neighbor anion. So let's try instead weighting the forces from a bunch of anyons in the system according to some power law, and hope that that weighting works out in such a way that on average I still move towards the guy that I'm supposed to be paired with. Right? And this was the idea of Harold et al. In their non-local decoder. Right? So for the purposes of examining this physics, let's try to make life easier by assuming that the measurements of the syndromes are perfect. And just for kind of ease of visualization here, let's assume that we have a power law interaction like this, which is actually just instantaneously set up between the anyons at each time step. So I know I spent this whole part of the beginning of the talk saying how we need everything to be local and finite speed in space, but right now we're just not going to care about that and assume that the field profile is set up as quickly as we like. Okay.
Is there a reason alpha is supposed to be strictly positive here?
Oh, why did I write alpha plus 1? Yeah. Just because I didn't write a unit vector on top, so I want this to scale as 1 over r to the alpha, but there's a...
Okay. Sorry.
And what we're going to do, as I said earlier, we're going to update the anion positions according to this law. So the direction in which the anions move is just going to be determined by the direction that the force is pointing, irrespective of its magnitude. Okay. So in addition to making our life easier by having perfect measurements and this instantaneous field that is being set up, we're also going to consider, for the purposes of this argument, a very friendly error model, certainly an overly friendly error model. The noise is basically only going to be allowed to create one long pair of anyons in the system. And once there's a well-separated pair, the only thing the noise can do is to create isolated nearest neighbor pairs at different locations. Okay. So we're going to restrict the power of the noise by only letting it do this kind of a thing. I hope you agree that we definitely want a threshold against this sort of friendly noise model. Under this noise model, we're going to focus on the separation between two anyons in this large pair. Right? What we need to do is we need to prevent these anyons from drifting apart and traveling around a cycle of the torus. Now, we're going to say just focus on the distance of this guy with respect to this guy. The force on this anion is going to be, there's going to be a deterministic part, which is an attraction towards the anion which it's paired with strength 1 over r to alpha. And then there's going to be a noise component, which is controlled by all the random pairs that have been injected into the system by the noise. Okay, so there's a deterministic part plus a random field. And the random field has this form, right? It's just, we're getting a random signal from all the other anyons that have been created by the noise. Okay. Now, the motion of this anion pair, we can just, all we care about is the radial separation between the two anyons in the pair. So we can map this problem onto a biased random walk on the line. So we have one member of the pair is sitting at the origin, the other member is over here. This guy is being attracted to the origin by this force, but there's also some noise that's acting on it, which is causing it to diffuse and jiggle around. Right. So if you like the diffusion equation that this guy is governed by, it can be shown to look like something like this. So this is a diffusion equation which has some bias towards the origin, in a way which is determined by the strength of this field. And then it also diffuses with some diffusion constant. So it's just biased diffusion on a half line, very simple problem. And you can